Hello guys, and welcome to another calculus video. In this video we're going to be solving these two cool trigonometric integrals involving cosine and integrated from negative infinity to infinity. So let's go ahead and jump right into it. So hopefully this first integral reminds us of the Fresnel integrals because we have that cosine of x squared and we're integrating from negative into infinity. The only difference here is we're taking the natural log, which makes it a little bit more difficult, but it's relatively easy to simplify. Now the first mistake would be trying to separate the natural log, because here we have integral from negative infinity to infinity, natural log 2 minus 2 cosine of x squared. Now the first thing that came to mind when I saw this was just to separate the natural log, and then we'd have integral from negative infinity to infinity of ln2 plus integral from negative infinity to infinity of ln 1 minus cosine of x squared. But clearly this doesn't work because this just diverges. So clearly there must be something balancing out in this other integral. So that's not what we want to do. We don't want to separate it that way. So instead, let's try reorganizing the inside. So 1 minus cosine of x can be rewritten in terms of sine of x over 2. So let's go ahead and do that instead. So we're going to end up with the integral from negative infinity to infinity of natural log of 4 sine squared of x squared over 2. And now this is a little bit easier to deal with, dx of course, and let's go ahead and rewrite this as 2 sine x squared, so 2 sine squared, and then we can bring that power to the front. So we're going to get 2 times the integral from negative infinity to infinity of natural log of absolute value of 2 sine of x squared over 2. And that absolute value is very important because otherwise we'd end up getting negative numbers in a place where that doesn't really make any sense. And of course our dx. Because obviously on the inside of the natural log here we have to have positive numbers. So that's what we have right here, and some of you may recognize this natural log of 2 sine x, and that's an actually very important identity. Natural log of the absolute value of 2 sine x is equal to negative the sum from n equals 1 to infinity of cosine 2nx over n. And this is relatively easy to show, so we're going to go ahead and do that in order to apply it to our integral. So let's go ahead and we're going to have natural log 2 sine x. This is the same as natural log of e to the ix minus e to the negative ix all over I, which is the same as ix, factoring out an ix, minus I pi over 2, plus natural log of 1 minus e to the negative 2ix. Just factoring everything out there. Then we're going to expand this as a power series. Just a reminder, we know that our overall answer is going to be real because we're talking about positive numbers here, natural log of a positive number, right? Because we really have this absolute value. So we don't need to worry about the imaginary part. So we're just going to worry about the real part. So we're going to have sum from n equals 1 to infinity of e to the 2ix, or e to the negative 2ix over n. And then a negative sign in front there. And of course, we're only talking about the real part, so this is going to be the sum from n equals 1 to infinity of cosine of 2nx over n. And that negative sign, of course, will remain right there. So now all we have to do is go ahead and plug it into our... Oh yeah, something else to note here is that the effect of putting this absolute value on the 2 sine x right here is that we go from having sine x looks usually like this, right? But when we add the absolute value, it's going to turn into something like this, and so that means it's going to be periodic, pi periodic, right? And notice that this function right here is also pi periodic, and if you replace x with x plus pi, you're going to get the exact same thing, and so that is kind of a good way to show that throwing that absolute value on there will allow us to still get the same answer. So let's go ahead and apply it to our integral. This is what we're going to end up after applying our formula. And then of course we're just going to let n x squared equal u squared, and that just means that square root n x equals u, and square root n dx equals du. So we're just going to be dividing by square root n. So we're going to get negative 2 sum from n equals 1 to infinity of 1 over n to the 3/2 times the integral from negative infinity to infinity of cosine of u squared, which is just the famous Fresnel integral. So when we go ahead and plug that in, we'll get negative sum from n equals 1 to infinity of 1 over n to the 3/2 times, so we're going to get square root pi over 2 like this. And this summation is just going to be zeta of 3/2. So overall, our answer is going to be negative square root 2 pi of zeta of, or times zeta of 3/2. So that's a pretty interesting integral right there. And let's go ahead and move on to our next integral. So our next integral is going to be a little bit similar. We're going to remain integrating from negative infinity to infinity, but instead we're going to have the integral from negative infinity to infinity of x squared cosine x minus 1 over x over x squared plus 1 squared dx. So immediately upon seeing this, this sort of reminds me, if instead of cosine x plus 1 over x, I just had cosine x right here, I would just go ahead and set up a contour integral, and that would be really helpful because integrating along a large semicircle, the outward semicircle would tend to 0, and all we would have to do is evaluate the residues. But since we have this negative 1 over x, we're going to have a really nasty essential singularity about 0, and so we have to be able to avoid that, and integrating around it, we're going to have a divergent integral. So it's an overall not going to work. So we have to figure out something else that's going to work. And so something else that we might be reminded of here is Glasser's master theorem, because we're integrating from negative infinity to infinity, and we have a function of x minus 1 over x. So we have to figure out how to turn the rest of this into something in terms of x minus 1 over x. So the important thing to notice here is that if we divide by x squared on the top and bottom, we get cosine x minus 1 over x over x plus 1 over x squared dx. And some of you may know, if you've tried to integrate square root tangent x, that this is a really helpful tool right here. We have that x plus 1 over x squared equals x minus 1 over x squared plus 4. Because if you notice, when we multiply these out, the x terms are going to be the same, the 1 over x squared terms, x squared terms. The only thing that's not going to be the same is we're going to have minus 2, and we're going to have plus 2 over here, so 2 minus 2. So we just need to add 4 right here. And so we can go ahead and rewrite this as the integral from negative infinity to infinity of cosine x minus 1 over x over x minus 1 over x squared plus 4 dx. And now, using Glasser's master theorem, or rather the special case of Glasser's master theorem, which is known as the Cauchy something something with an s theorem, we can rewrite this as the integral from negative infinity to infinity of cosine x over x squared plus 4. And now this is a relatively easy integral to go ahead and do. We're going to substitute x equals 2u, so we're going to end up with 2 times the integral from negative infinity to infinity of cosine of 2u over 4u squared plus 4. Divide that 4 out, so we're just going to get 1/2 on the outside. And then this is just going to become 1, all du. And then this is a very famous integral. The formula in question, which can be obtained using contour integration, is the integral from negative infinity to infinity of cosine of au over u squared plus 1 du is equal to pi times e to the negative absolute value of a. In this case, our value of a is 2. So overall, our integral is going to be equal to pi over 2 e squared. So overall, yeah, that's the answer to that question. I hope you guys enjoyed these cool integrals that I solved in this video. If you want to see more like this, just let me know. If you have any suggestions, please leave them down in the comments. So yeah, hope you guys enjoyed the video, and I'll see you next time.